Well, welcome to Lecture 14, everybody.
So polyatomic ions are essentially molecules that have covalent bonds between the atoms. However, most of them needed extra electrons, or in one case it actually had to lose electrons, in order to form the necessary bonds. Because it gained extra electrons, or lost an electron, they ended up with a charge on them, and so they behave as kind of a superion, a very large, polyatomic, many-atomed ion. And these are generally made up of nonmetals. We do have a couple that have metals in them. Now, the easiest way to recognize an ionic compound that has a polyatomic ion in there is to see that we've got more than two types of element in the compound, and one of those is going to be a metal. We're still going to have a metal, non-metal concept here in general. However, we have more than two types of element in the compound. We do have some exceptions, with one of those being a metal, where we can actually have all nonmetals and still have an ionic compound, and we'll take a look at that in class as well. Well, here's your list of polyatomic ions from your book. You want to make sure that you're familiar with a lot of these, and because a lot of these are very common and they show up a lot in our compounds, and you don't want to have to look them up every single time that you see a polyatomic ion in an example. Let's take a look at some examples, and again, we're going to work these out in class. So we have potassium nitrate, iron 2 phosphate, Li2CO3. We see there that we've got three different types of atoms, so it's a good indication that we have a polyatomic ion. And then we have Cr2 SO4 3. And so there we have also three types of atoms in there, so a good indication that we have a polyatomic ion. You're certainly welcome to try those on your own before class or after class, but we will go through those examples during class time.
The first thing that we want to talk about is molecular compounds. Now, in a molecular compound, it's a little bit different than what we have in an ionic compound. In a molecular compound, our individual atoms are held to each other by covalent bond. Now, if you remember, in a covalent bond, we have our electrons being shared between two atoms. Now, Lewis structures for each atom can be used to determine the number of bonds that each atom wants to form. And then we can take those dot structures of the individual atoms to see how atoms are going to fit together. Now we have some different types of bonds. We have single bonds, and in a single bond, this is where we have just one pair of electrons being shared between atoms. Generally, we have each atom contributing one electron to that bond, and so between the two atoms, they actually have two shared atoms, and that creates a bond between those two atoms. And so the pairs of electrons that form bonds in a dot structure for a molecule, we call those bonding pairs. And any pairs that are not involved in bonding are called lone pairs. Now, not all atoms in all molecules have lone pairs. Generally, it's only going to be the atoms that are from group 5 or through 7a, so 5a, 6a, and 7a, that will have lone pairs when they form compounds. Let's take a look at dot structures for molecules. So one of the things that we can do is to draw a dot structure for each atom, and then find a way to make all the atoms share unpaired electrons, form an octet around themselves, and so that all atoms have an octet around them. So some examples we'll look at in class. One is F2, and another is HClO. We'll also take a look at 7 diatomic gases. There are 7 gases in the periodic table similar to F2 that are diatomic, and we'll take a look at a way of learning how to determine which of the gases in the periodic table are diatomic. Now, sometimes sharing one pair of electrons does not lead to an octet, and what you may have to do, or what an atom may have to do, is to share more than one pair of electrons. And when you do that, you lead to multiple bonds. So each pair of electrons that gets shared is considered a bond. So in something like O2, We'll take a look to see how that's made in class, but what we'll find is that we have two pairs of electrons being shared. And when they do that, both atoms fill their octet, and since we have two pairs being shared, we have what is called a double bond. If we were sharing three pairs of electrons, such as nitrogen does, well then we have a triple bond. So it just depends on how many pairs of electrons are being shared between two atoms. Now once we've made our molecules, we want to figure out a way to name them. Now our binary covalent compounds, these are what are going to be making most of our molecules, and they're generally made using two nonmetals. And we name them in a similar fashion than we did for ionic compounds. The only key is that we can't use charges for a formula if we're going from a chemical formula to a name. So we can't use charges for that formula. Or we can't go from a name to a formula either because of charges. So several different possibilities exist for any given two elements. So just an example of that, nitrogen and oxygen is always a very common example. We could have NO, could have NO2, we could have N2O, could have N2O3, N2O4, N2O5, and there's probably some others as well. So just the term nitrogen oxide for a compound formed between nitrogen and oxygen would be very difficult to name just using the elemental names. So what we do is we use Greek prefixes to indicate how many of each element are present. And so usually what we have is a prefix, some kind of Greek prefix that indicates the number, and then the name of the first element, just like we had for ionic compounds, and then another prefix here for our second element, and then just like in our second elements, we have the base name of that second element plus the IDE, just like we had for ionic compounds. So here's our table for our Greek prefixes, and many of these you'll be familiar with. Mono is equal to 1, di is equal to 2, tri is 3, tetra is 4. That may be one you haven't seen before. Once you hit 5, they're always pretty much the same. You see some different prefixes for different uses for 1, 2, 3, and 4. However, once you hit 5, 6, 7, 8, 9, and 10, they're generally pretty much the same. For naming purposes, for our molecular compounds, we use mono, di, tri, and tetra. Now, since both our atoms are nonmetals, how do we know which of those elements is going to go first in our chemical compound? In an ionic compound, we always put the metal first. Well, since these are both nonmetals, that doesn't help. So what we do is we look at a property that's called electronegativity, and we haven't learned that yet. It's going to come up in a future chapter, so for now, we're just going to kind of leave it alone. But you put the least electronegative element first with that element name. And again, that's coming in a later chapter, so we don't have to worry about that just yet. And as we saw on the previous slide, that second element is still given an IDE. Now, one exception we have to this naming convention is that we never use mono on the first atom. If there's only one of that first atom, we don't put mono, we don't put any prefix, we just use its name, and that tells us that there's just one of that first atom. Let's take a look at some examples here. So we have CO, so we have carbon, and then just one oxygen, so we call that carbon monoxide. We have CO2, again we just have that one carbon, we don't put monocarbon, so we just say carbon, and then there's two oxygens, so 2 has a prefix of di, so carbon dioxide. Our next compound, SF6, again I just have one of that sulfur, so I say sulfur, and then I have 6 fluorines, and so that comes in as hexafluoride, so sulfur hexafluoride. Now, our very last one here, N2O5, I've got 2 nitrogens, 5 oxygens, so I do have to put a prefix before that nitrogen. So I say dinitrogen, telling me I have 2 nitrogens, pentoxide tells me I have 5 oxygens. Now we can look at formula mass and molar mass. So we're starting to get a little more into the quantitative aspect of our chemical formulas. So the formula mass of a molecule, or if it's an ionic, if I'm looking for an ionic unit, we express its formula mass in AMUs. And all we do to find the formula mass of a molecule or an ionic unit is to take the atomic mass of the average atomic mass for each element in there, multiply it by the number of those elements listed in the formula, and add it all together. Well, as it turns out, the molar mass of a compound is expressed in grams per mole, and we saw that the atomic mass for each element, if you had a mole of that compound, is the same number in grams as one atom would be expressed in AMUs. So for a compound, all we do is add up the sum of all the molar masses of each atom in that compound. We multiply each of those atoms by the number that is present in the formula, and we add it all together, and we get the molar mass. So if we were to look at that in the equation, we say the formula mass or the molar mass is going to be equal to number of atoms of the first element times the atomic mass of the first element plus number of atoms of the second element times the atomic mass of the second element, etc., for however many elements you happen to have in a chemical formula. What can we do with that? Well, we can start to use that molar mass to convert between grams and moles. We've seen how to do that for individual atoms back in an earlier chapter, and now we can do it for molecules and formula masses for ionic compounds as well. So we convert between grams and moles by using the atomic mass, and then we use Avogadro's number to convert between moles and number of atoms. And once again, we can do the exact same thing using a compound's molar mass in order to get the number of molecules. Take a look at just a graphic here. And so what we've got here is we've got our mass in grams. We can convert from grams to moles using the molar mass, and we can convert from moles to number of atoms using Avogadro's number. I can go back from number of atoms to number of moles using Avogadro's number, and I can go from moles back to grams using molar mass. Notice that I cannot go from mass to number of atoms, and I can't go from number of atoms directly to mass. You just can't do that, so don't even try. The reason is because your atoms have different sizes and they have different masses, and so there's no way to go from number of atoms to mass in grams. It would be just like saying going from pieces of fruit to how much the fruit weighs. Without knowing which fruit you're using or how much each piece of fruit weighs, you have no possible way of doing that. Well, here's an example that we're going to work out in class. We want to know how many molecules of water are in 0.4 grams of water. Let's look at chemical composition. Whenever we're trying to identify an unknown chemical compound, normally what we do first is to try to find its chemical composition. And these types of analyses usually express each element in some sort of mass percent, or maybe even in the actual mass of each element in your particular sample. So we can take a look here, and if we want to calculate the mass of a particular element that we would expect to find in a given compound, so here we have CCl2F2, which is a chlorofluorocarbon. We would have that the mass percent of chlorine would be equal to 2 times the molar mass of Cl. And the reason we have 2 times that is because there's 2 moles of chlorine in each mole of that molecule. So we'd say 2 times that molar mass over the molar mass of this whole compound. Now to get the molar mass of this whole compound, I would take molar mass of carbon plus twice the molar mass of chlorine plus twice the molar mass of fluorine. If we want to see that worked out, say that the mass percent of chlorine is equal to twice the molar mass of chlorine over molar mass of the whole molecule itself times 100%. So we say 2 times 35.45 grams per mole. We got that value from the periodic table. To find the molar mass of the chlorofluorocarbon, we see we have 1 carbon. Whoops. Let me go back there. There we go. So we have 1 carbon at 12.01 grams per mole. I have 2 chlorines at 35.45 grams per mole. And I have 2 fluorines at 19 grams per mole. So we work out that math times 100%, and we find that this compound is 58.64% chlorine by mass. So the chlorine atoms in this compound make up 58.64% of the mass of this compound. Now what can we do knowing that? Well, we can still use molar mass and use it as a conversion factor, kind of going back the other way, to find out how much of a particular element is in a given amount of a particular compound. So as an example, how much oxygen gets used up to form 100 grams of carbon dioxide? Sorry, got a typo there. And this is something that we'll work out in class as well. Well, that finishes out Lecture 14. I hope you found this useful. There is a little bit more calculational information in this lecture, so if you need to, go back, re-watch the material. If it's still not making any sense after this and after lecture, make sure that you come see us for some help.